Okay, so in this video, I'm going to prove actually a theorem from an earlier section that we skipped over before because I felt like it wasn't really relevant back then, but it is now, about how integration interacts with uniform convergence for sequences of functions, okay? So we've seen examples, right? We've seen examples where Fn converges to F pointwise on, let's say AB, but the integral from A to B of Fn does not converge to the integral from A to B of F, okay? We've seen examples of this. We've actually seen a couple examples of this. And what happens is that, in the pointwise convergence, what happens is that like Fn, each of the Fn's is able to kind of maintain some kind of constant area, but then the area under the graph of Fn keeps getting like squished into a smaller and smaller place and getting like concentrated on a specific part of the interval, so that it ends up vanishing completely in the limit, even though it's actually, there's like a constant amount of area in the actual sequence itself. So uniform convergence prevents this. Okay, so that's what we're going to prove. Theorem 25.2. So the statement is this: let Fn be a sequence of, and I'm going to say integrable functions. Okay, the actual statement in the book uses continuous here, but integrable is actually what's appropriate, and it's a weaker condition. So this theorem, I mean, the proof doesn't change at all. It's just like this statement is actually more general than what they say in the book. I think it might be either a typo or they just didn't want to use the term integrable. I'm not sure. So Fn is a sequence of integrable functions on an interval AB. And suppose Fn converges to F uniformly on AB. Then the limit as n goes to infinity of the integral from A to B of Fn equals, I guess, Fn of x dx if you want. I prefer not to use that notation, but that's what they use in the book. Equals the integral from A to B of f of x dx, okay? So you can basically pass, the limit can pass through the integral, right? You can move the limit from outside to inside. So you can basically take the limit of the functions first and then integrate, rather than integrating all the functions and then taking the limit. You're not allowed to do that with pointwise convergence, right? So I'm going to draw a sketch real quick of the basic idea of why this is true, because it's actually very straightforward. All right, so here's a picture which basically shows you how the area between, or like the error between the integrals of f of x and the integral of Fn of x is related to the actual sort of pointwise distance between f of x and Fn of x, right? Because the point is that like we can make Fn of x stay within this sort of ribbon here, right, all the way on the entire interval AB, right? So if you think about like the width of this ribbon is epsilon, and the point is that the possible error, the possible distance between like the integral of f of x and the integral of Fn of x, if Fn of x is trapped in this ribbon, then like the biggest difference, the biggest that like the area between the two graphs could be is if Fn of x was like all the way up here, or Fn of x was like all the way down here, and it's the same in either case. Basically, the idea is that epsilon, like whatever the difference between f of x and Fn of x is, the bound on that, right? That bound, multiplying that by the width of the interval gives you an upper bound on the difference in the integrals, basically. Okay, so that's the sort of intuitive idea that guides the proof here. So the way the proof goes is like this. So okay, let epsilon greater than 0. Now epsilon over here was like the epsilon we control. Maybe it'd be better to call this like epsilon 2. Right? So we're able to like control epsilon 2. We can pick epsilon 2 and force Fn to be close to F, right? Because we know that Fn converges uniformly to F. So the point is that if we choose epsilon 2 so that like epsilon 2 times b minus a is less than the given epsilon, then we can say that the integral of Fn of x is within epsilon of the integral of f. So that's what I'm going to do here. So we let epsilon be greater than 0. This is how close we want the integrals to be to each other, right? So then set epsilon 2 to be like epsilon over b minus a, and pick capital N such that for all n greater than capital N and for all x in AB, we have the absolute value of Fn of x minus f of x is less than epsilon 2, right? Then what we have is that the absolute value of the difference between the integrals, and I'm going to use some facts about integrals here that we haven't quite proved yet, but yeah, just trust me that these are true. So the integral from a to b of Fn of x dx minus the integral from a to b of f of x dx equals the absolute value of the integral from a to b of, or sorry, yeah, the absolute value of the integral from a to b of Fn of x minus f of x dx. This is linearity of integrals. And then this is less than or equal to the integral from a to b of the absolute value of Fn of x minus f of x dx, which in turn is less than or equal to the integral from a to b of epsilon over b minus a, right? Because this is less than or equal to epsilon 2, which equals epsilon over b minus a. And then this just equals epsilon, right? So, well, actually, this is, I guess this is like strictly less than. So anyway, you know, there you go, right? So the two things here, so this step uses the linearity of integrals. So in general, the integral from a to b of f dx plus the integral from a to b of g dx equals the integral from a to b of f plus g dx, right? So that's one thing. And then this one is a theorem. It's the triangle inequality for integrals. So we will prove this later. Basically that you can move an absolute value outside of an integral into the integral and you'll get an inequality that way. So, yep, that's theorem 25.2. So with that out of the way, so now we know that uniformly convergent sequences preserve integrals in the limit. So with that out of the way, then in the next couple of videos, I'll show how we can integrate and differentiate power series term by term.